Eric.
Oh, okay, more people coming on. I see Tristan, I see Ezra. Hello. Oh, Tudor, hi. Oh, Tudor's on the train, that's right, awesome. Melanie, I can't scroll to see everybody, unfortunately. But it's fun. Who I can see is it? Marco.
Sheldon, are you hosting?
No, I am. Ron, can you make me the host again?
You're not the host? I did not change anything.
I had to give it to you so that you could turn on the streaming thing. You know, all this tedious stuff.
Oh, okay. Hold on a second.
Hi, Ron.
Eric, good to see you.
Yeah.
Was in.
Bring you on.
Harry.
Hi.
Did that work?
Yes, it worked.
Yeah, that's good. Thank you. Perfect. Maybe I'll wait just one more minute, Eric, if that's okay.
Great.
Are you ready now, Eric?
Yep, sure.
All right. So then, so we're very happy to have, welcome again to the Western Hemisphere Colloquium in Geometry and Physics. We're very happy today to have Eric Zaslow, who will speak about framing duality. And Eric has asked that if you have questions during the talk, you just shout them right out. And of course, there will be a period for questions at the end of the talk. And I will also, Eric provided some notes, which I will paste into the chat momentarily. All right, take it away.
Thanks, Andy. It's an honor to give this talk, and it's a pleasure to see so many familiar faces. This is joint work with Gus. This is joint work with Gus Schrader and Linhui Shen that I'll be talking about. So the goal of this, also you'll see the notes in chat, hopefully soon, and or you can, this is being recorded so you can watch it double time, but I'll be directing for those who are listening in real time. The goal here is to calculate conjectural open Gromov-Witten invariants of a class of Lagrangian branes. In C3 by exploiting cluster theory. The warning here is that well, this work overlaps the work of many others. And in some sense, it's a synthesis of other people's work. And I will highlight those people. Some of them are on this Zoom here. Okay, so I want to begin with some of the physics. And I sometimes have problems with the screen share. So if it freezes, just please jump in and let me know, and I'll have to reshare. Okay, the physics of the story is calculating the partition function of 3D n equals 2 theory. resulting from an M5 brane filling 3 dimensions and a Lagrangian. The Lagrangian we'll take to be inside C3. That's an n=2 theory. And this theory was studied in different, using different methods by several groups. Cordoba, Ciccati, and Vafa, Cordoba, Espabodi, Hagigat, Rastogi, Vafa in one setting, and Dimufte, Gabella, Gayoto, Gukov, Dimufte, Gabella, Gontra in another setting. This group studied the 3D theory based on an ideal triangulation of the manifold. And this group here studied cases where the M5 brane was a branched cover over a ball. Roughly speaking, the difference is this branch cover is like a spectral curve for this theory here. Both cases had a sort of basic, both treatments had a kind of basic case. On the one side was an ideal hyperbolic tetrahedron. And on the other side, the brane was branched over 2 strands like this. In both cases, the 3D theory was the abelian n=2 Chern-Simons theory with one chiral multiplet. And the partition function of that is known through supersymmetric localization. The partition function depends on the moduli of the brane. Okay, so that's one lesson to us, is that we're going to have to understand the moduli of the theory. And we'll be studying that moduli space using sheaf theoretic methods. Okay. There's another context in which similar calculations result, but in understanding open Gromov-Witten theory, Aganagich and Vafa studied disk invariants by looking at a D6 brane wrapping R4 cross L. In this case, the effective theory is 4-dimensional n=1 theory, and they calculated the superpotential W of this theory. They calculated it using mirror symmetry by recognizing the mirror brane, a B brane, who had a moduli space that you could more easily study because it wasn't corrected. And the effective holomorphic Chern-Simons theory reduced on that brane resulted in the superpotential. A higher genus treatment was later taken up by Uguri and Vafa, and they calculated the higher couplings of this 2D n=2 theory. So related to higher genus open Gromov-Witten invariance and integrality. And they did that by studying a D4 brane on R2 cross L, so an effective 2-dimensional theory. And the M theory setup of that in the strong coupling limit is a phi brane on R3 cross L. So you see the same theory arising. And that's telling us that these partition functions maybe are related to open Gromov-Witten invariance. And that will be sort of our take on things. As I said, Aganagich and Vafa studied the mirror symmetry. So the mirror of these branes were B branes, and they calculated the superpotential from holomorphic Chern-Simons theory reduced on those branes. Okay, so Aganagich Vafa's lesson for us is that the superpotential is computed by seeing how the moduli space sits in some kind of period domain. Let me just remind us how that worked out for Aganagich and Vafa, because that's what we're going to copy for more general moduli spaces. Okay, so this is the Aganagich-Waffe example. Actually, they studied the resolved conifold. Later, Aganagich, Clem, and Waffe studied the case of just C3, and we'll study just C3. So here's our first sort of geometric setup. We have C3. I've written it in its toric moment map. So that's like the corner of the room. Absolute value of x squared, absolute value of y squared, absolute value of z squared. The Lagrangian that they consider is a toric one. It's invariant under a U1 symmetry. And you get it by looking at a ray in the moment map image being a ray and in the direction of 1, 1, 1. So this ray extends in the direction 1, 1, 1. And it ends at one of the corners here. So out here at a generic point, the pre-image is the full three-dimensional torus, but we take the Lagrangian pre-image, so that's a two-dimensional torus. And but the pre-image, one of those circles in the two torus shrinks. So it becomes a solid torus, which is a T2 shrinking to a circle in the core of the torus. This is the special Lagrangian studied by Harvey and Lawson. And here's an explicit parametrization of it. So if you take the ray to end at the origin here, you actually get a cone because both cycles of the torus collapse. And this is an explicit parametrization of the special Lagrangian cone, where S and T are torus parameters. The smooth Lagrangian is this has this parametrization. You replace one of these r's by square root of r squared plus epsilon. So that's measuring sort of the size of this circle. Okay, the mirror of that story, the mirror of C3 is this threefold. AB equals x plus y minus 1, where A and B are C variables, and x and y are C star variables. The mirror brane to this brane here is the brane where B equals 0 and A is free. And because the left-hand side equals 0, the right-hand side has to be equal 0 as well. So x and y are have to be taken to be a point on this so-called mirror curve. And then therefore that mirror curve is the moduli space of these branes. So that curve is a pair of pants. You see the pair of, this is a picture of the moduli space. And why is it a pair of pants on the mirror side? Well, the position of this brane can vary this way. And there's a non-trivial S1 in the brane. So we choose a local system on the S1. So we get a cylinder here, out here. And there's a cylinder of moduli here. If we had chosen to resolve this coordinate. And this coordinate would give us another cylinder. So we have something that looks like three cylinders. And the size of the disk instant time corrections is non-trivial in the middle. So they're somehow sort of merged in some mysterious quantum way, which makes the moduli space of the brane hard to study on the A side, but on the B side, it's easy to study. Okay, and just to remind us, how does that connect to open Gromov-Witten invariants? Well, these x and y are C star coordinates. If we look at their logarithms, U and V, the U and V are conjugate variables. And then we solve for V in terms of U. So I take the y equals 1 minus x. So take the logarithm of that, V equals minus log of 1 minus e to the u. And Aganagich-Waffe, by looking at the reduced holomorphic Chern-Simon series, say to write V as the derivative with respect to u of the superpotential, and then we get the dilogarithm here. It's basically the definition of the dilogarithm. And this dilogarithm is then the superpotential, which tells us that there's a single sort of primitive disk, and then multiple covers of that. So this is the written as the sum x to the n over n squared being the multiple cover formula for disks.
Could I ask a quick question?
Please, thank you.
Are the three legs of the, what labels can I attach? It looks to me like your three legs of your pants corresponded to maybe the three axes, or I just want to
yes,
if
yes,
they have names.
they correspond to the three axes. So sort of if we had resolved, this is one smoothing of the Harvey-Lawson cone, where I replace this r by r squared plus epsilon squared. If I had replaced this one or this one, we would have gotten the other smoothing. So if that ray had ended on the other branches.
Okay, so I can think of this as a pair of pants with labeled pants.
Yes, in fact, these three these 3 points at the end of the pair of pants, maybe sort of cusp points, are sort of three directions of expansion of this superpotential. Sort of choosing the small coordinate to expand the superpotential in. Okay, other questions? Okay. So Aganagic, Clem, and Waffe that later studied many more examples of this beyond C3. Other examples that have that are not exact have non-trivial symplectic forms, although C3 is all we will study today. And they also clarified the dependence on the framing and the phase. So the phase are those three smoothings that we were just discussing. And the framing is another choice. Basically, when you need to write, let me go back, one coordinate as the derivative with respect to another, this depends on the choice of coordinates, canonical coordinates, so to speak. And different such choices lead to different functions. And that's the famous framing dependence of open Gromov-Witten invariants, and also phase dependence. Okay. Another related study was by Aganagic, Ekholm, Eng, and Waffe, where they studied the, again, the resolved conifold, looking at the large N duality. That's where the framing gets its name, by duality with Chern-Simons theory. And they showed how to compute how higher genus open Gromov-Witten invariants were related to augmentations of the corresponding Chicana-Villey-Ashburg DGA of the not conormal. Augmentations relate to sheaves, and sheaves relate to Fukaya objects. So again, they're studying essentially the moduli space of branes. So let me show what happens, how higher genus is incorporated. It's incorporated in the fact that this U and V are conjugate variables. So let's go back to this equation for the moduli space. And this higher genus was also studied by Aganagic, Dijkgraaf, Clem, Marino, and Waffe. You'll notice a lot of Waffes here. Andy and I are mathematical brethren, both supervised by Hermann Waffe, and his stamp is all over this work. Okay, so we'll recall that X was exponential coordinate, Y was exponential coordinate, and U and V are conjugate variables. And you can see that, for example, in the effective Chern-Simons theory. And so if V is conjugate to U, it's minus IH bar d by du. So I can write this as e to the IH bar d by du. And so the action of Y, well, let's take a wave function to be function of X. So the under quantization, x acts by multiplication. Let's say we choose that polarization, and y will act by Taylor series. This is a translation of u. So y of f of x is equal to f of u. Sorry, should write this as e to the u plus I h bar, which I can write as f of qx, where if I define q as e to the I h bar. So y acts by shifting the argument. X acts multiplicatively. So we can solve this equation. Let me just see. Yeah, I think I want to solve it down here. So I left myself some space. So I'm going to take this. Let's just put it down. Take this equation and solve it. And what we're going to get is some wave function. Maybe I'll solve it first and then discuss why I'm calling it a wave function. So I wanted to solve y equals 1 minus x. And that means solving. I'm going to now use wave function notation. Y changes x to qx. And psi. We can solve this equation. And a sort of algebraic solution, there's more than one solution, and that will come back to haunt us. But here's an algebraic solution. So this is just 1 over 1 minus x times 1 over 1 minus qx times. And you see that if you replace x by qx in this formula, then you pick up the infinite product from the second term. And so you've multiplied the answer by 1 minus x. So we solve this equation here. Okay, so let me discuss a little bit about the wave function interpretation of things. Witten interpreted the BCOV equations for higher genus closed Gromov-Witten invariants as being the equations for a wave function in a Hilbert space for the quantization of the moduli of the Calabi-Yau. So he reinterpreted those equations as the equations for a consistent quantization over the moduli space, where the moduli space is essentially the space of polarizations of the third cohomology group of the Calabi-Yau. So the lesson maybe there's such a similar interpretation for open Gromov-Witten invariants, although I don't really understand the TT star equations in the open setting. Maybe there is such an interpretation, and the higher genus open Gromov-Witten invariants are controlled by studying the quantization of the moduli space of the brane. Wave function interpretation for the partition function of the 3D n equals 2 theory that I mentioned earlier was taken up by this group here. And they also showed that the dependence on moduli looks like a wave function. So that's maybe indications that this is sort of appropriate interpretation of these sort of non-commutative equations that describe the moduli space. Wave function, Aganaga, Jacome, and Wafa, the example that we just studied, also discuss the wave function interpretation. So we're going to see that we have a moduli space. We want to see how it sits inside a period domain, how it gets quantized, and then try to solve the quantization equations. Okay, I did mention, before I get going on doing all that, I did mention the framing dependence being different coordinates. So in framing P, this equation looks like x to xy to the 1 minus P plus y equals 1. And the above is framing 1. So that has completely different solutions, and and likewise the open Gromov-Witten invariants are completely different when you change the framing. Let me also study the logarithm of psi. So that'll be a sum of minus logarithm of 1 minus q to the n. So it'll be a sum over n. And expanding that second logarithm, sum over m, qx to the, whoops, qx to the m, so that's q to the nm, x to the m over m. That's the expansion of minus log 1 minus x. And now we can resum and write this as sum over, what do I want to sum over here? N now. And now multiplying both numerator and denominator by q to the n, n over, sorry, I'm summing over n. So that's a q to the m. Multiplying numerator and denominator by q to the m over 2. What do I have? I have a sum over m. Xq to the 1/2. So let's interpret this as something to the m over m times, now replacing q by e to the ih bar sine of mh bar over 2. And this is the Ugori-Baffa higher genus multiple cover formula. So again, we have a primitive disk and all of its multiple covers. And this quantized solution to the equations describing the moduli space is giving the higher genus Gromov-Witten invariants. So what did we do? We've found this moduli space in this quantization. Maybe I'll write down the quantization here, y x equals q x y. And we solved the equation and we got the higher genus open Gromov-Witten solutions. Any questions? Wow, Ken interrogator, hi. Okay, so that'll be our plan. Define a large class of brains. They will be labeled by a graph. Understand phases. We saw phases already in the Harvey-Lawson example. Framings, choices of coordinates. We want to sit the moduli space inside some sort of period domain. And then the part that I haven't discussed yet, exploit the cluster structure to compute these wave functions and make connections, to open Gromov-Witten invariants and other things. All right, so that's the plan of the talk, halfway in. All right, so let's get going. First, the label of the Lagrangians is going to be a cubic planar. Sorry, I think I might have this written down already on the next page. Here we go. The label of the Lagrangian will be a cubic planar graph. So that's this red part here. And how do you construct a Lagrangian from that? Well, I'll show you how. You take a sort of two-sheeted cover of the graph. And that's drawn in purple here, this sort of two-sheeted potato chip. And the two sheets are crossing each other over the graph. So I hope that's visible here. You see the two sheets crossing here, and they cross over the whole disk and meet down there. This picture, this potato chip, is a picture of the front of a Legendrian. And the Lagrangian will be a cone over that Legendrian. And then we'll smooth that cone just as we did in the Harvey-Lawson example. So the two sheets will be plus and minus z, and the crossing locus will be when z equals 0. How do you make a Legendrian out of that? Well, it's the standard construction. The Legendrian will sit inside R5 or inside S5. And that's at the boundary of C3. And the extra coordinates for R5 in this local picture are the y's, and the yi's are dz dxi. So that makes a Legendrian. So what about in the Harvey-Lawson example? I'll remind you, what was the Legendrian at infinity? It was a torus. I'll remind you of the parametrization. Parametrization was e to the I s, e to the I t, e to the minus I s plus t. The potato chip in this case has height z equals this thing, sine 2s plus sine 2t minus sine 2s plus t. And z equals 0 when s equals 0 or pi, or t equals 0 or pi, or s plus t equals 0 or pi. You can check that. So on the T2, there are these lines. And the map to S2 is a double cover map. It's just inversion on the torus in this example. And then these lines cover this tetrahedron inside S2. So the cubic graph in the Harvey-Lawson example, this basic example, is the tetrahedron. And this is, well, actually dual to that tetrahedron case studied by Dycraft et al. Sorry, Dimofte et al. Sorry, tutor. Okay. So for the Lagrangian, we're going to take any Lagrangian filling whose boundary in an appropriate sense at infinity is this Legendrian, labeled by this graph. Okay, what about the phase and the framing? So the choices of coordinates that we'll need. Well, the homology at infinity injects into the homology of the Lagrangian, and we'll take it to be a surjection, so we're not going to introduce any topology. And sort of that's in the language of the triangulation studied by Dimofte et al. Means we'll take an ideal triangulation. And that will define the phase. The phase will be the kernel of this map. And you'll recall that that phase is going to label which of the cycles collapses. So if you take resolve the singularity in the x direction, one of the cycles on the torus will collapse in the y in the z direction. Basically, if you write the homology lattice of the torus, the three phases would be, here, here, and there. Okay, and the framing will be a splitting of this, so a choice of the other coordinates. So the phase labeled the small coordinate v in our language, and the other coordinate we called u, but because v is small, you can't really identify u. You could take u plus pv, and that would also be a large coordinate. And these are both Lagrangian or isotropic directions in the homology lattice of the Lagrangian. Sorry, it's too many Lagrangians. We have a Lagrangian. It has a Legendrian at infinity. Its homology lattice has a symplectic structure by the intersection form. And so these two, the directions of collapse is isotropic in that symplectic structure. And then we want a transverse isotropic direction. So an isotropic splitting. That will be the definition of phase and framing for us. Okay, so we've constructed from a cubic graph a Legendrian. We are going to be considering Lagrangian fillings. A little bit of if the Legendrian is genus G, there'll be 3G plus 3 edges, a little bit of combinatorics. You'll recall that the branch points of the cover of the sphere were the vertices. And so when you have a line between branch points, you get a loop upstairs, just as you do in solving complex equations. So these loops generate the homology lattice, but there are relations. Each face gives a relation, and here's the relation. Just the sum over the edges of the face is 0. By the way, you don't need to orient the edges. This loop has a canonical orientation upstairs. So when you go like this, you get a natural orientation. Okay, and a proposition says that this is the homology lattice. It's the edges mod faces, gives the homology lattice of Legendrian. Now we need to construct the Lagrangian filling. So how do we do that? So first, let me draw the cone. So here's a picture of the tetrahedron. And we saw that gave a Legendrian torus. And the singular Harvey-Lawson Lagrangian was a cone over this thing. So I've just taken a cone in the 3-ball over the boundary sphere. And then you see that we get, so the resulting thing will be a Lagrangian threefold, and it will be a branch double cover over the ball, branched over the cones over the branch points at the boundary. So that'll be 4 lines, 4 rays joined at a point. The smooth Harvey-Lawson is a resolution of that point. So that'll be the branching locus, and that will be the smooth tangle. Here's another example. This is a genus 2 example. So we have a triangular pyramid. And just as cubic graphs are dual to triangulations, so these pictures that we'll fill them with will be dual to tetrahedronizations. So I've drawn here the dual picture. The dual of the prism is the bipyramid, 2 tetrahedrons stacked on top of each other. And if there are famously sort of 2 different ways of choosing triangulations of this bipyramid, one with 3 tetrahedra, one with 2 tetrahedra. And I've drawn the one with 3 tetrahedra here. So you get a tetrahedron like this, and there are 3 such. Dually, here's the dual picture of that tetrahedronization. It's what we call a foam. It has these faces like that. Lines are dual to faces in 3 dimensions. So what you do is you create such a foam, and then you smooth it by doing a Harvey-Lawson smoothing at each vertex of the foam. And then you'll get a tangle, and you get lots of tangles this way. So that's all the ingredients that you need. We've constructed a Lagrangian filling through this combinatorial object and its smoothing. And what we need to do is now describe how does the boundary at infinity, the homology lattice, map to the homology of the smoothing. Let me show you a picture of how to do that. Well, again, if you take a arc in between the branch points, you'll get a loop upstairs. You have a double cover branched over this tangle. And if you have a map from one strand to another, you get a loop upstairs. And those loops generate the homology lattice of the Lagrangian filling. There are relations in those loops, and here's the relation. Here are the relations in the loop. If you have an internal face, then you get a relation among the arcs in that face. So this gray face is an internal face, and that tells us that B and C are going to be related. And here there's an interesting sign in the relation. So given a face and an arc, there's a relative sign that you can construct. I don't know, I think it's kind of interesting. So I'm going to draw it. So you go like this. And then at the start of the arc, you have one vector in the direction of the face. And at the end of the arc, you have another vector in the direction of the face. So let's say call it VI, VJ, and call the vector in the direction of the arc V. And then you take the sign of the determinant of V, VI, VJ. And if you had oriented the arc from the other side, you would have gotten the same sign. Okay, so now this describes the homology lattice of the Lagrangian. And now we need to show how to the edges at the boundary inject or surject onto the arcs. And then, so the exterior faces of this foam give us an equation like that. I guess I won't go through all the details of that equation, unless there are questions. Okay, so that's the geometric setup. We've constructed Legendrians at infinity. We've constructed Lagrangian fillings. We understand how the homology lattices relate to one another. We have a definition of phase and framing, which allows us to construct coordinates on some moduli space that we haven't constructed yet. So that's the next thing up, construct the moduli space. Okay, so the moduli space of branes, what are the branes? Well, the Lagrangian branes are objects in a Fukaya category where we impose an asymptotic condition on the brane. This was studied by many people. David Nadler and myself and many others studied such a situation and interpret the Fukaya category as a category of constructible sheaves with micro support on the Legendrian, the asymptotic boundary. So that will be the moduli space here. It's the moduli space of objects in this category of constructible sheaves, micro supported on this Legendrian with some decorations, microlocal rank 1. So I want to explain how to work with such categories. So let me first do an example in a sort of dimensionally reduced example. Take a point cross R. So that'll be a line. And what it would be, she is micro supported on these three Legendrian directions. So Legendrian just means sort of directions. So I'll give you points and directions. This 0 here in the definition means I want the sheaves to start at 0 down at R equals minus infinity. This 1 in the definition means I want the rank of the sheaf to jump by 1 across each place where the Legendrian sits. So singular support is the jumping locus for locally constant sheaves. And so what I'm saying is that the rank of the stalks should jump by 1. That's this one, each time you cross the Legendrian. Okay, so I've just described an object in this category. It's a flag. It's something with zero-dimensional vector space and one-dimensional vector space and two-dimensional vector space and three-dimensional vector space. And the restriction maps of the sheaf will give you the maps, which will be inclusions. So you actually do get a flag. Here's another example, R cross R. I'm just going to cross this by R. So you get like that. The Legendrian directions would point down. And we get 0, 1, 2, a flag. It'll always be a flag because I'm just crossing with a contractible space. So in R2 cross R, which is the dimensions relevant to the example, 0, 1, 2. Okay, so the moduli space is a moduli space of flags. There's a little bit of, there's a nice piece to add to that, which is what happens at these crossings. You'll recall that in our dimensions, we had these sheets and they crossed over these cubic graphs. What happens over the edge of a cubic graph? Well, that's a crossing. And the requirement is that the flags have to be transverse at the crossing. That's not a definition, that's a consequence of this. I mean, it's not, I'm not imposing it artificially, it's a consequence of this definition. Okay, so the flags are different. And in this amount of dimensions, this is a line in two-dimensional space. This has to be a transverse line in two-dimensional space. Or in other words, a point in P1 over here, a different point in P1 over there. Okay, so that's the whole moduli space. It's a moduli space of flag colorings of the graph. So you have a graph, cubic graph. In each face, over each face is something like this. Actually, not this many sheets, just 2 sheets. So you have a two-dimensional flag or point in P1. And a neighboring flag must be distinct, so a different point in P1, because this edge represents a crossing of the 2 sheets. Okay, so that's the definition of the moduli space. Flag colorings of the map defined by gamma. Okay, so let's see, how does that work in our basic tetrahedron example? There's the tetrahedron. Let me draw it as a planar graph that looks like this. Up to PGL2, I can take 3 of these points to be 0, 1, and infinity. And this other point has to be different from, because this face label is adjacent to all the other points, this Z has to be different from 0, 1, and infinity. And therefore we get the pair of pants, just as in the Lagrangian case. Does not require mirror symmetry. We just did the whole thing using the moduli space of A-branes. Okay, now how does this sit? How does this moduli space sit inside a period domain? Well, we have a functor actually from sheaves to micro-supported on lambda to local systems on lambda. And at the level of moduli spaces, that means that our moduli space will sit inside the moduli space of local systems on the Legendrian surface. Surface being genus G. Surface local systems on that will be a torus of dimension 2G. Just like in the Lagrangian case, G was 1, and we set things inside C star squared. So we'll do that here. The map is the one defined by Falk and Goncharov. It's also, we don't need to define it, it's a consequence of this definition here, that you have this map automatically. The local system on this loop defined by the edge will produce a holonomy, and the holonomy will be the cluster coordinate X, and X is the cross ratio of the 4 P1 points in P1 of the 4 regions around it. X will not equal 0 or infinity because these points cannot be equal to their neighbors. So the cross ratio will live inside C star, as it should. Okay, so maybe a good time to pause for questions. We've set everything up. We have now a moduli. We have the branes are defined by cubic graphs. We have their moduli space, which will be flags, 1 in each face, or points in P1 in each face in this dimension. We understand how it sits inside a period domain. We understand the phase and the framing, namely understanding how the homology lattice of the Lagrangian and the Legendrian boundary relate. And now we just need to solve a bunch of equations and quantize them. Okay, what are the equations that cut out the image of this map? So you have to write them down, and here they are. Each face gives an equation. And here's the equation on each face. So each face, if you label the edges counterclockwise, there's a corresponding coordinate for those edges, as we discussed above. And this is the equation that you write down. There's also a constraint on you take these cross ratios around this loop, their product is -1 to the n being the number of edges in the face. So each face gives this constraint and this equation. You'll recall that there were 3g plus 3 edges and g plus 3 faces. So 2g is the number of edges minus these face constraints. So that was the dimension of local systems on the Legendrian surface. And these are the g constraints that cut out dimension g subspace. So those are the equations. Okay, now what happens under mutation is that one torus becomes another torus, and the whole shebang describes a cluster, a symplectic cluster X variety. Okay, let's see how that goes. So what happens when we change the Legendrian? Cluster theory says that these edge coordinates get related to these coordinates here. And those cluster transformations can also be done in the sheaf world as well, as we showed in with Vivek Shendi and David Truman and Harold Williams. But the mutation itself is done by Fak and Gontrev in the cluster language. All of this gets quantized. So the quantization, which we saw in the canonical coordinates of Aganagach and Vafa, looks like this. We saw what yx equals qxy, but more generally, these labels, x's, are labeled by the edges, which are labeled homology directions in the Legendrian surface. That has a symplectic pairing, and that determines the quantization. And these cluster transformations also get quantized. So here's Q, and I put Q in the cluster transformation. The commutation rules follow from the effective Chern-Simons theory. Okay. So for each cubic graph, we had a moduli space, but they sew together because we saw that when we mutated the graph, we got a different Legendrian, but we could relate coordinates between them through this cluster transformation. And lo and behold, this is as shown by de Mufte, Gontrev, and Gobella, these equations are consistent. So if you take these coordinates and mutate them, you get new equations, and they're the same. So let me see if I can show you an example of that. So try to be very concrete. So suppose you were on this face here. You'd have something like 1 minus z plus zs and other stuff. Then you mutate, you get this stuff here. You'd have, this will go to 1 minus QZ. Wait, sorry. That Q I put in the wrong place. All right. So now I have to go 1 minus this up plus this times QX inverse. Like that. Okay, and does that equal? Yes, it does. But when I prepared these notes, I was a little bit more on top of my algebra than I am right now. So I don't. It's a little bit hard to see right now. I think it's probably easier if I had done maybe this one instead. So I would have had 1 minus S plus SX minus SXY. And what would that turn into? 1 minus S times 1 minus X plus S times 1 minus X times X inverse. Okay, this one I think is more manageable. The other one you can do, it just takes a little bit more of commuting. Expanding that and writing this as multiplying numerator and denominator by X, I get X over X minus 1. And so this is plus S times minus X, Y. And then it's true. All right, so the other ones are true, but maybe not as simple as this one. So those equations transform into the equations. The whole thing becomes something which makes sense globally. And there's the global picture. You have this symplectic cluster variety, P, which is Borel decorated PGL2 local systems that are unipotent at the G+3 punctures, which were the faces of the cubic graph. In each cubic graph, you get a chart. And in each chart, you have a moduli space. Those glue together to form a global Lagrangian quantized moduli space. And these are just the local systems with trivial monodrom. We want to find out, given a phase and framing, what the wave function is, and conjecture that it's the open Gromov-Witten invariants of the Lagrangian. But the nice thing is that the mutation rules are just given by conjugation by a quantum dilogarithm. So if you know the chart, if you know the wave function in one patch, you can mutate it and get the wave function in other patches where maybe you don't know it. And there's a nice space where you do know it, namely it's an exact Lagrangian. And if it's exact, there are no holomorphic disks and the wave function is identically 1. And so that's the plan. We start out with a wave function that we know, we mutate to wave functions that we don't know, we conjecture that those are open Gromov-Witten invariants. So here's a little bit more on that. Here's the conjugation. The cluster mutation is given by conjugation by the quantum dilogarithm. And therefore we can compute the wave function in another chart. The problem is that I might have written this wave function in some coordinate, y, and x might not be sort of mutually local to y, right? X and y might not commute. And so I might need to write this operator, re-express the result of this operator on this wave function in terms of the mutually commuting variables associated to the phase and framing that I wanted. So that makes it a little bit delicate because you might go from an x variable to a y variable. That's a symplectic transformation that relates u and v, let's say, conjugate variables. And that will be Fourier transform. And this algebraic quantum dilogarithm, you can't really Fourier transform it. it's an expansion in a small variable that is no longer small in the Fourier transform. So you have to go to the analytic version, which is the so-called non-compact quantum dial algorithm. And that's the proper partition function of this basic 3D theory with one 3n equals 2 abelian Chern-Simon theory with one chiral multiple. So the physics tells you that that is the right thing to consider. But it actually makes the calculations quite a bit harder, although the consistency checks quite a bit more robust. Okay, so maybe time to say what the results of all this are. We conjecture that the wave function that you get when you write it in terms of the coordinates of your phase and framing has an integral expansion corresponding to Orgori-Vafa integrality in terms of non-compact quantum dial algorithms. And the logarithm of this wave function is the open Gromov-Witten generating function of the corresponding Lagrangian filling. The bootstrap is to say that if we begin with this graph, which is a Chicana related to the Chicana torus, is what we call the Chicana surface, it has an exact Lagrangian filling, so we know its wave function, and then that's a good starting point. And any other graph is related by mutations. There's another result, which is framing duality. I guess I'll just state it, and then if there are any questions after the time, because I'm at my time limit, then I can take them then. Framing duality is this strange relationship, which you can see is true by looking at formulas for DT invariants of quivers derived by Kontsevich and Soibelman. It turns out that if you take this canoe graph, this one here, here's a canoe. It's got G seats, these horizontal bars. And you take some standard phase for it, namely the one that you get by mutating this necklace graph around the strands of the necklace. The framing is related, is defined by a G by G symmetric matrix, integer symmetric matrix. Then you can ask, well, what's its wave function? What's the algebraic version of the wave function? Namely, when you turn those non-compact quantum dial algorithm into the standard quantum dial algorithm. Well, it's something, and it turns out it's the DT invariance of some quiver. The quiver whose adjacency matrix is actually this G by G symmetric matrix. So that's what we call framing duality. The different choices of framings define different quivers and different DT invariants, and they also define different open Gromov-Witten invariants, and those correspond. In the genus 1 case, this was also seen by Luo and Zhu, although our construction generalizes to these arbitrary genus cases. Okay, so that's the end. You have this open Gromov-Witten conjecture. You have a method of computing, and you have this duality with DT invariance of quivers. So thanks.
Great. Let's thank Eric. Thank the speaker. And now we have time for some questions. And in fact, there was a question in the chat earlier on from Tudor and John. I think Tudor's on a train, and so I don't want to make him talk. But maybe John, do you want to speak out?
Or you can.
Sure. The question was, why are points in these? Why should the faces be labeled by points in P1?
Ah, great. Thanks. Yeah, I'm still sharing the screen. So here is the moduli space. It's the moduli space of these constructible sheaves. The input is this Legendrian, and that tells us where the stalks of the sheaves can change. So if you recall, the wavefront of the Legendrian surface was some sort of two-sheeted cover of the sphere. So here's a picture of that. So looking up from the sphere, you encounter one sheet and then another sheet and then another sheet. And each time you encounter a sheet, the stock of the corresponding sheaf has to jump by 1. So as you move up, you get a 0-dimensional vector space and a 1-dimensional vector space and a 2-dimensional vector space. And in fact, for us, we only are considering 2-sheeted covers, so there's no more sheets. So it goes like that. So we have this flag 0, 1, 2. Up to PGL2, the 2-dimensional vector space we can take to be C2. And so the whole data is defined by just a line in C2 or a point in P1. And that's what happens sort of above each face of the graph. So you have a point in P1 for each face. Does that help? I see two.
Definitely, thanks. So if you have more sheets in your cover, you get a flag, like a longer flag?
Yes, exactly.
Okay, thanks.
The combinatorics of constructing the Lagrangian filling by, becomes considerably more complicated. I think that in their work they know what to do for a so-called N triangulation or K triangulation. Yeah, I'll just leave it at that.
Great. Other questions? Tudor typed another question. He says, changing framing should be like a Fourier transform, and do you know how to make that precise?
Yes. Okay, so changing framing is in Fourier transformation. So let me find some blank space. So the symplectic group is generated by things like this. That's changing framing. Things like this. That's simply your sort of choice of, that's change of coordinates is a simple one. And then this one here. Okay, so this one's easy. This does not involve Fourier transformation. And there's an explicit change of framing formula that you can use Concevich-Soibelman's change of framing formula, and it preserves integrality. It's known to do that. This one is easy to do. It's just change of basis. This one is Fourier transformation, and it corresponds to change of phase, actually, not change of framing. This is the hard one, and it's why we need to work with the non-compact quantum Dell algorithm. So it's not obvious that if you have a wave function like, I don't know, maybe that's your wave function, and now you want to do a Fourier transform and write it as psi, maybe V1, V2. It's not obvious that these two are the same. Okay, there are some identities among Fourier transforms of non-compact quantum Dell algorithms, which say that which you can use to in various examples to show that the wave functions agree when you do these transformations. But I don't know anything more general that says if you have I don't know how to, maybe something like, maybe this is your wave function. And then you do Fourier transform on that, and you try to write that as some product. It's not clear that integrality will be preserved. And so the best that we can do right now is check some examples and find that there are some relations among Fourier transforms of products of non-compact quantum Dell algorithms that work out. But it'd be great to have something more general. It's a great question. It's in fact why I've probably spoke on this several years ago, and it's why the paper isn't out yet, because of precisely this question. And it's also a lot of the heft that Gus Schrader brings to the collaboration is these kinds of calculations. I also wanted to mention that it is a strange time to be giving such a talk. That action of the X and Y variables I learned from Boris Segan, a wonderful Ukrainian mathematician colleague of mine that I'm thinking a lot of these days.
I also have a question. You said that one way to think about what you're doing is that you're conjecturally computing Gromov-Witten, open Gromov-Witten invariants. In this context, are those Gromov-Witten invariants defined?
No, they're not rigorously defined. Typically, they have a definition. Well, in some contexts, they're defined. And when the brain has a U1 symmetry, they're defined through localization typically. That's the Aganaga-Schwaffe case. But these other brains that I'm defining with these cubic planar graphs do not have such a symmetry. I'm told by Jake Solomon and Sarah Tukachinsky that the definition of that we give of phase and framing is exactly what you would need to make them well-defined. Although their work so far hasn't been on the non-compact case. So I think that those foundations still need to be developed mathematically. I know Vito Iacovino has also worked on this.
Great. Well, if there are no other questions, let's thank the speaker again.
Thanks a lot for the invitation. Great to see so many familiar faces out there and names.
And so the next colloquium is in 2 weeks, and the speaker will be Jörg Teschner. So hope to see you there.
Thanks, Andy. Thanks, everyone.
Right now, I'll stop the recording and the.
Thanks, Eric.